Okay, welcome back, fourth grade. I hope that you found part one of this video very helpful. This is part two. So we are going to review about charge and static electricity. Then we're going to talk about electrical discharge and then move on to talking about conductors and insulators. So make sure that once again you have that packet that you used in part one because I am continuing in the same packet. Make sure that you also have a pencil ready and take notes on your packet. Do not take notes on a separate piece of paper. And as always, as you're playing this video, you can always pause and work on it at your own pace. Do not feel like you have to rush through it. You can even review it more than once if that helps. So in part one of this video, we talked about how all objects around us have positively charged particles and negatively charged particles as well. And this includes us humans. We also have these charges. So that's why we talked about in the case with the balloon and the hair, there were those positively charged particles in the girl's hair that were attracted to the negatively charged particles that were in the balloon. Positively charged particles will attract negatively charged particles, or we can also say negatively charged particles will attract positively charged particles. So opposites will attract like charges, a negative and a negative, or a positive and a positive push each other away. Negatively charged particles tend to move more freely than positively charged particles. And once again, when you look at example 3 today, we're going to see this as well. So, what is static electricity? We started talking about static electricity in part 1. This is what caused the girl's hair to stand up. So, a buildup of electrical charges on an object is called static electricity. So when the balloon was rubbed on the wool, there was a buildup of charge, right? We said that negatively charged particles tend to move more freely than positively charged particles, and this is what was happening in the balloon. So let's look on page 124. At the bottom on the left, it's page 124 in your packet. Under what is electricity? The balloons that are shown in the figure, they show a neutral balloon. If you notice on the neutral balloon, it's neutral because it has 5 positive charged particles and 5 negatively charged particles. So like I said in part 1, they cancel out each other. So one positive charge will attract a negative charge, so on and so forth. Therefore, they cancel out each other. However, if you look at balloon 2, it's positively charged because it has way more positively charged particles than negatively charged particles. So that's 5 versus 2. Balloon number 3 is negatively charged because it has more negatively charged particles than positively charged particles. It has 7 negatively charged particles versus 5 positively charged particles. So this is what causes the difference in these different balloons. And if you notice, the neutral balloon is not attracted to anything. It's just in its own stationary position. However, the negatively charged and positively charged balloons are attracted to each other. Once again, opposite charges will attract. So my negative charges in balloon 3 are attracting the positive charges in balloon 2. That's why the two balloons are close together. Let's do the quick check. Why are the two balloons in the diagram attracting? Take a minute and think about what I just said. Remember, opposite charges, my positive and my negative, are going to attract. And if you notice in my two balloons, the positively charged particles are moving much closer in balloon 2 to balloon 3 because they're being attracted by the negative charges in balloon 3. Now you may wonder, how come the negative charges in the first balloon are not attracting positive charges in the second one? Once again, balloon 1 is neutral. So all the charges are equal number, so they cancel out each other, meaning there are not any more that can attract any other charge in another object. Turn over your packet to page 125. We're going to talk about rubbing and movement of charge. Rubbing causes charge in an object to move. When the balloon was rubbed on the girl's sweater, charge moved from the wool sweater to the balloon. In the example given on page 125 of your packet, we see that there is charge in the balloon and there is charge in the wall. Now you may be wondering, how is there charge in the wall? Remember that all objects around us have charge within them. This could be your ruler, this is you, all objects around us, as long as they have matter or that in those states of matter that we have talked about, they have charge. However, we don't walk around seeing electricity sparking on different objects randomly because once again, in a neutral state, those charges cancel out each other. It's only when there's rubbing that you can actually see the activity caused by these charges. So example 2 shows that charge moves within the wall, even though the wall does not move. So in our first example, the girl's hair was moving. In this particular example, the wall is not moving, but charge inside the wall is moving. We only see movement by the balloon moving close to the wall and sticking to the wall because those positively charged particles in the wall, as you can see in your diagram, are being attracted to the negatively charged particles in the balloon. That's what's causing it to stick. So positive charge is attracted to the negative charge in the balloon, and negative charge in the wall is repelled from the negative charge in the balloon. So if you see when you look at the wall, all the negatively charged particles are on the other side of the positively charged particles because there is no way that the negative charges in the balloon can attract the negative charges in the wall. They push each other away. Let's look at the quick check before we move on to page 126. It says complete the main idea diagram. This is on your paper. List 2 details that help explain the main idea. The main idea on this page is that the balloon sticks to the wall. And we can say because negative charge is attracted to positive charge in the wall, the balloon will stick. And we can also say that the rubbing caused negative charge to build up in the balloon. So at first, the balloon did not have as much negative charges as it has in our diagram. It needed to be rubbed against something else, which in this case is wool, for it to have more negative charges in it. So when you go back to your notes on your paper on page 125, it says, think of what happens when you try this. Rub a balloon with wool. Rubbing causes a buildup of negative charges on the balloon. So the balloon doesn't just decide to have more charges. You had to have rubbed it against wool for it to actually have more negative charges. Because remember, negative charge moves more freely than positive charge. Let's move on to page 126. And remember, if you at any point you feel like I'm going too fast, you can always pause, read your packet, replay the video, and then move on. In this page, we're looking at example number 3, talking about electrical discharge, the finger and the doorknob. I'm sure many of us have experienced this. This happens a lot, right? Sometimes it's not when you touch a doorknob, it could even be maybe when you reach to touch a friend. Somehow there's that spark and you feel that little shock. And that's because you may have been dragging your feet across the floor and picking up that charge. So let's look at this scenario. As you walk across a carpet, your feet are rubbing against the carpet. If you notice here, it seems that we always need some kind of rubbing for us to get more charge in an object. Remember, most objects are neutral. That means the charges are canceling out each other. When we rub one object against another, that's when there's that movement of charge, and one object gets more charge than the other. Charge moves from the carpet to you, not just your feet. The charge moves to you. And this is why it's not going to be you touching your friend with your foot. It's going to be you literally reaching out to touch your friend that you experience that shock. You now have more negative charge in you than before. When you reach for the doorknob, what do you think happens? I think we have all already experienced this. When you reach for that doorknob, the negative charge in you attracts the positive charge in the doorknob. Remember, the doorknob also has charge. So we may see a spark and then you experience a shock. Electrical discharge is this movement of charge from you to another object, which is the doorknob. Take a look at this figure here on my slide. You can see in the finger that a whole lot of negatively charged particles. However, in the rest of the hand, you can see that positive charges are also there, but we definitely have more negative charges than we do positive charges. When you go to touch the doorknob, those negative charges attract the positively charged particles. And this is where now we see that or feel that spark or that shock. Let's do the quick chat before we move on to conductors and insulators. Correct each of these false statements or sentences. This is on page 126 at the bottom of the page. Statement number 7 says, you become positively charged when you walk across a rug. We know the statement is false, but why is it false? When I'm dragging my feet across the floor, do I become more positively charged? Take a look at my figure on the PowerPoint. In A, we see that I actually become more negatively charged. So when I go and reach for the doorknob, the negative charge in me attracts the positive charge in the doorknob. So the correct statement should be, you become negatively charged, right? Because the negative charged particles move from the carpet and build up on your body, not just on your feet, but in your body. You feel a shock when negative particles move from the doorknob to your hand. We know that this statement is false. Why is it false? This statement is false because the negative particles are not moving from the doorknob, they're moving from your hand. So the word doorknob and hand should actually be flipped to say, you feel a shock when negative particles move from your hand to the doorknob. Now we're going to talk a little bit about conductors and insulators. This is page 127 in your packet. We said that charge flows in a circuit. Remember, a circuit is the path for charge to flow. and it needs to be a complete circle, not a perfect circle, but it needs to be a closed path. It cannot be open for my charge to flow. So we need materials that allow charge to flow. In a little bit, we're going to look at a circuit and look at where conductors are and where insulators could be placed. So conductors are those materials that allow charge to flow easily. These are all my wires that I used in my circuit. Those allow my charge to flow easily through them. And most of the time, it's going to be a copper wire or it's going to be silver. All my appliances that I use, whether it's a phone charger, whether it's a drill, whether it's my computer cords, whether it's my laptop charger, all of these actually have wires in them. Also, your headphones, right? So my headphones that I connect, maybe I plug them into my phone, I plug them into my iPad, I plug them into my laptop. All of those have wires in them. And these wires actually help charge to flow, right? Because when I just touch my um headphones, I don't feel any shock or feel any charge or anything like that. It needs to be connected to something to make that circuit. We're gonna look at that in a little bit. Insulators are those materials that do not allow charge to flow easily. However, we need insulators for safety purposes. We cover our conducting wires with insulating materials to prevent shock. As you notice, when you walk around your house, hopefully you shouldn't see any wires exposed. That is very dangerous because you can actually get shocked. And sometimes it can even cause a fire. So all my wires around my house should be insulated with plastic. And for most of my wires, it's actually going to be a black plastic. So today, walk around the house and look at how many devices or gadgets or appliances around the house you can find that actually have insulating materials around them. Most of the time, they're going to use plastic, but glass, rubber, wood, all those are insulators because charge cannot flow through them. So let me exit here and we're going to take a look at my circuit. This is on my vocabulary page. So this is my circuit. My circuit, like I said, should be closed. As you observe here, there are actually no openings in this circuit here. I have a wire over here. I have a wire over here. And then I also have a wire over here. And if you notice, it notes here that all these wires are conductors. But most of the time, I'm not just going to see exposed wires. My wires are going to be covered with an insulating material, such as plastic, so that I don't get shocked. For example, your phone charger. If you take a look at it, that wire is covered with a plastic. So you are not going to see the wire. Unless, of course, maybe something happens and there's some kind of break in the insulating material, then that's when you'll start seeing exposed wires. And most of the time when that happens, the charger maybe stops working or doesn't work well. So my wires do need that insulator so they're not affected and my charge can flow freely. Let me go back here to my slide. Let's do the quick check. The quick check on page 127. In each row, cross out the word or words that do not belong. Number 9. The words are conductor, glass, copper, silver, and let charges flow. Which one here does not belong? If you say glass, you are absolutely correct. Glass is not a conductor. It does not let charges flow easily through it. It is an insulator. Let's look at question 10. Insulator, copper, rubber does not let charges flow. Which one does not belong? If he said copper, you are absolutely correct. Copper is actually a conductor, it is not an insulator. So all my wires around the house, like I said, if you take a walk after watching this video, you will notice that they're all covered with plastic because plastic prevents charge from flowing. So if I touch my charger, if I touch the kettle cord, if I touch the cord for the toaster or the cord for the microwave, I'm not gonna get shocked as long as that insulator is covering the wire. The wire is the one that carries my electricity, if I were to say it that way. So my insulator cannot carry any electricity. It prevents the electricity from shocking me. So ladies, that is it for part 2. The next part, we're going to be looking at electric circuits. Make sure that you have your vocabulary list with you as we'll go through that first before we learn about different kinds of circuits. Have a wonderful day.